subsidence is the motion of a surface as it shifts downward relative to a datum such as sea level. The opposite of subsidence is uplift, which results in an increase in elevation. Ground subsidence is of concern to geologists, geotechnical engineers and surveyors. Dissolution of limestone. Subsidence frequently causes major problems in karst terrains, where dissolution of limestone by fluid flow in the subsurface causes the creation of voids. If the roof of these voids becomes too weak, it can collapse and the overlying rock and earth will fall into the space, causing subsidence at the surface. This type of subsidence can result in sinkholes which can be many hundreds of meters deep. Mining. Several types of subsurface mining, and specifically methods which intentionally cause the extracted void to collapse, will result in surface subsidence. Mining-induced subsidence is relatively predictable in its magnitude, manifestation and extent, except where a sudden pillar or near-surface underground tunnel collapse occurs. Mining-induced subsidence is nearly always very localized to the surface above the mined area, plus a margin around the outside. The vertical magnitude of the subsidence itself typically does not cause problems, except in the case of drainage or rather, it is the associated surface compressive and tensile strains, curvature, tilts and horizontal displacement that are the cause of the worst damage to the natural environment, buildings and infrastructure. Where mining activity is planned, mining-induced subsidence can be successfully managed if there is cooperation from all of the stakeholders. This is accomplished through a combination of careful mine planning, the taking of preventive measures, and the carrying out of repairs post-mining. Extraction of natural gas. If natural gas is extracted from a natural gas field, the initial pressure in the field will drop over the years. The gas pressure also supports the soil layers above the field. If the pressure drops, the soil pressure increases and this leads to subsidence at the ground level. Since exploitation of the Slochteren gas fields started in the late 1960s, the ground level over a 250 km² area has dropped by a current maximum of 30 centimeters. Earthquake. The Geospatial Information Authority of Japan reported immediate subsidence caused by the 2011 Tohoku earthquake. In northern Japan, subsidence of 0.50 m was observed on the coast of the Pacific Ocean in Miyako, Tohoku, while Ryukyu Takata, Iwate measured 0.84 m. In the south at Zama, Fukushima, 0.29 m was observed. The maximum amount of subsidence was 1.2 m, coupled with horizontal dystrophism of up to 5.3 m on the Oshika Peninsula in Miyagi Prefecture. Groundwater-related subsidence. The habitation of lowlands, such as coastal or delta plains, requires drainage. The resulting aeration of the soil leads to the oxidation of its organic components, such as peat, and this decomposition process may cause significant land subsidence. This applies especially when groundwater levels are periodically adapted to subsidence, in order to maintain desired unsaturated zone depths, exposing more and more peat to oxygen. In addition to this, drained soils consolidate as a result of increased effective stress. In this way, land subsidence has the potential of becoming self-perpetuating, having rates up to 5 centimeters per year. Water management used to be tuned primarily to factors such as crop optimization, but, to varying extents, avoiding subsidence has come to be taken into account as well. Faulting induced. When differential stresses exist in the earth, these can be accommodated either by geological faulting in the brittle crust, or by ductile flow in the hotter and more fluid mantle. Where faults occur, absolute subsidence may occur in the hanging wall of normal faults. In reverse, or thrust, faults, relative subsidence may be measured in the footwall. Isostatic subsidence. The crust floats buoyantly in the plastic asthenosphere, with a ratio of mass below the surface in proportion to its own density and the density of the asthenosphere. If mass is added to a local area of the crust subsides to compensate and maintain isostatic balance. The opposite effect in isostatic subsidence is known as isostatic rebound, the action of the crust returning to a state of isostasy, such as after the melting of large ice sheets or the drying up of large lakes after the last ice age. Lake Bonneville is a famous example of isostatic rebound. Due to the weight of the water once held in the lake, the Earth's crust subsided nearly 200 feet to maintain equilibrium. When the lake dried up, the crust rebounded. Today at modern Lake Bonneville, the center of the former lake is about 200 feet higher than the former lake edges. Seasonal effects. Many soils contain significant proportions of clay which because of the very small particle size are affected by changes in soil moisture content. Seasonal drying of the soil results in a reduction in soil volume and a lowering of the soil surface. If building foundations are above the level to which the seasonal drying reaches, they will move, and this can result in damage to the building in the form of tapering cracks. Trees and other vegetation can have a significant local effect on seasonal drying of soils. Over a number of years, accumulative drying occurs as the tree grows. This can lead to the opposite of subsidence, known as heave or swelling of the soil, when the tree declines or is felled. As the cumulative moisture deficit is reversed, over a period which can last as many as 25 years, the surface level around the tree will rise and expand laterally. This is often more damaging to buildings unless the foundations have been strengthened or designed to cope with the effect. See also, lateral and subjacent support is a related concept in real property law. Cave-in. References. External links.